Uh, Good morning, all. Welcome back to our, this is the third day. Let us welcome Professor Fineberg, who would be talking about fast and slow fractures. And he's coming from Raka Institute. And let us all welcome.
Thank you.
Please, go ahead, sir.
Okay, so a number of things. First of all, we'll be switching gears a little bit this morning in two ways. Number one is the talks that I've heard have been incredibly high level. Today we're going to lower the level. Okay, so this will make the other talks sound much better. So it's a double-edged sword. Another thing is we're switching scales for a little bit. Okay, so I'll be talking about things that are quite far from many of the topics that we're talking about in the school. Now, I'm a physicist, and we do a good job of teaching physics at the Hebrew University, I think. But nowhere that I've seen in a physics curriculum is any talk about fraction, which is kind of strange because it's like an everyday thing all around us. So, you know, it's mostly designated. I mean, there's a community of active community physicists that play around with breaking things, but usually engineers try to stop breaking things. That's where the physics and engineering communities actually separate. Oh God. Okay. Okay. Anyway, so let me start with the onset of the modern theory of fracture. And by the way, I'll be giving a series of 3 talks. So today I'll be talking about simple fracture. What that means, you'll see in a minute. Tomorrow I'll talk about when fracture doesn't obey the rule book. So things that simple fracture or the established theory of fracture doesn't explain, not yet at least. And the third talk, I'll be switching gears entirely, but not so much. I'll be talking about the physics of friction and the physics of earthquakes. So if you feel the earth move, probably not because of my talk, but that's another story. But you'll see that this stuff and those seemingly disconnected topics are very much the same. And that's the topic of my third talk. So, okay. So where is the modern basis of fracture comes from? It's actually because of this or things like this. This is the USS Schenectady. I practiced in front of the mirror a number of times till I got it right. Okay, now you've probably never heard of the USS Schenectady, and there's a good reason for that, because this is one of a series of what were called Liberty ships that the US, in order to supply the war effort during the Second World War to Europe, they made them in an assembly line fashion. And what happened was that a large percentage of these things, you know, when they took the champagne bottle and christened it the USS Schenectady, the minute they put it in the water, it broke in half. Now, this was considered a problem by some. So they brought together some of the greatest minds in physics to try to understand how to prevent this. There were other projects during World War II that were much more successful. One that you probably heard about is the Manhattan Project. Successful or not is a matter of philosophy, but actually they got to where they wanted to go. This project is still ongoing, so I'll tell you a little bit about it. But the first theory of dynamic fracture was developed by Sir Neville Mott, and this was actually only declassified. It was part of the war effort, of course. So it was only declassified in 1948 or so. So the whole idea, everything I'll be talking about is relatively new. And it's still ongoing in many ways. So as you see, we have slightly larger scales we're talking about than many of the talks here. But we'll find out that actually all the good stuff happens at very small scales. Fracture is a multi-scale problem. And you'll see in a minute what I mean, which makes it interesting and a bit difficult sometimes. Okay, so I went backwards or forwards or something. Okay, so first I want to tell you why cracks are interesting, and then I'll briefly tell you about how they're supposed to behave according to the standard theories or classical theories. And then we'll have a happy, this is a manic depressive talk. Okay, so the happy part now is that I'll show you that yes, they work when they're supposed to work. The theory is wonderful and everybody can go home. But then I'll show you when things stop working. These are crack instabilities, which are not included in standard theories of fracture, not even in unstandard theories of fracture. That's when nature stops reading the textbooks. Then I'll try to zoom in on these things by talking about fast fracture in slow motion. So gels were mentioned earlier. What we'll be doing is looking at soft materials. Maybe that's why I'm here, soft materials or something, whatever. In soft materials, they have many characteristics, but the one that's useful here is that they're soft. So the speeds of sound are now meters a second instead of kilometers a second. So we can say very rapid effects in slow motion and hopefully understand them. And then I'll finish with a new theory for nonlinear fracture mechanics. So this will be a non-trivial extension of the classical theory, which I'll talk about here. By the way, just stop me with questions or comments or whatever during the talk. It's fine. There's no exam at the end of the talk or anything. We don't have to cover specific material. So if there's something that you don't understand, probably there are other people that don't understand it as well. And quite possibly the lecturer doesn't understand it. So feel free to ask questions and we'll take it from there. Okay, so why should we study fracture at all? Well, first, it's kind of neat to be paid to break things for a living, but there are no number of fundamental open questions. For example, why are some materials brittle, like glass, where others you make buildings out of, or cars? The elastic properties of this and that are virtually the same. So what's the difference between a brittle material and a ductile material, or something that's useful and something that's also useful for other things, but not necessarily for building cars? I'll show you that the theory of dynamic brittle fracture is incomplete. And these are some of the important unresolved questions. So first of all, the criterion for where the crack decides to go. You know, crack starts to move, okay, to where? I'll talk a little bit about that. And then what happens when a crack, which we kind of, I'll talk about the theories in a two-dimensional world where we're looking at a one-dimensional branch cut or defect that's running through the material. But what happens when that one-dimensional material or the one-dimensional point at the tip of a crack becomes spatially extended, so it's a crack front? What happens if you break the crack front? And again, this is kind of this classic study of theory of fracture is a spherical cow, and little by little we're starting to make it an elliptical cow or something of that nature. Okay. How did things break? Well, naive approach is you stretch something, you apply a force, and you can pull the atoms, molecules, grains, or whatever apart in a homogeneous way. And if you pull them far enough, then they'll disassociate. So that makes sense. That's how things could break. Now, if you do that, so here's a potential between particles, atoms, whatever. And if you do the calculation, you find that approximately a 50% strain is needed in order to break something. So if you pull things homogeneously, slowly, you'll have to stretch it by 50% in order for dissociation to start. Okay, that's fine. Things can break that way. But something's wrong in this picture because usually already at a 1% strain, things fracture. So we have a 2 orders of magnitude difference between the naive approach and what happens for real. And let's see why. And the reason was given by Inglis in 1913, when actually he took a 2-dimensional sheet of material. Again, I'll be ignoring for a while this 3rd dimension here. So we're looking at a 2-dimensional world. And he put in an elliptical defect into the material, and then calculated what the stresses are. So the stress here, the applied stress, is totally uniform. What the stresses are at the tips of the long axis of the ellipse. And this is what he found. So the stress was amplified by this factor. So it's 2 times the length of this ellipse divided by the curvature at its tip to the power of 1/2. Okay, so this makes things. Now, what happens though if we start to take this ellipse and start to squash it? So the curvature here gets larger and larger, or the radius of curvature gets smaller and smaller. And so what we find is that if we take the limit of squashing this ellipse to a straight line, the stress at the tips of the crack, this is now a crack, are singular. In fact, they go as some factor K, which the experts call the stress intensity factor, divided by the distance R from the tip of the crack to the 1/2 power. So as R goes to 0, the stresses at the tip of the crack become singular. So this is the reason that things break at much less stress than one would naively calculate. And the reason is because of this is an honest to God real world singularity. And anytime you have a defect in a material crack, you're going to get that singularity at its tip. Now, you're all familiar with similar things. Some of you might be familiar with the singularities in black holes. Not talking about that, but we're all familiar from 1st year physics with the singularity of the electric field at the tip of a point electrode. So the pointier you get, the higher the field is. This is slightly different physics, but it's the same idea. So we have so what cracks do is they focus the elastic energy that's being applied at the boundaries into this singularity. So bonds now are not broken uniformly, but in a very efficient manner, kind of like dominoes. So this stress singularity will break the material bond after bond right at the tip. And it makes materials much weaker. So, okay, the bottom line is the existence of a crack leads to a large decrease in a material's effective strength. Okay, now I'll sketch on, I'm an Israeli, so we tend to sketch things, we talk on what's called on 1 foot. So if you can, if you're not unable to explain something while you're standing on 1 foot, according to some of our sages, you really don't understand it. So I'll try to give you the quick overview of what's in the theory of fracture, where it comes from. And this theory of fracture is called linear elastic fracture mechanics. And what it is, and I won't go through it here, but the theoretical background here is that you have wave equations in the bulk, two wave equations, because we have a shear and compressive waves. And they're only coupled at the boundaries. So all of fracture, if you actually solve the problem, is given by solving two uncoupled wave equations that are coupled on the boundary. And the boundary is very non-trivial. We have a free stresses in back of the crack because it's broken, so there aren't any stresses in its wake. And there's something called mixed boundary conditions. In front of the crack, you have a displacement condition, how stretched it is. And solving that will give you what I'll tell you about in a minute. So the main assumptions are that we're talking about small strains. That's where the linear elastic part comes in from the linear elastic fracture mechanics. So the strains in the material are all very small. And there's an assumption that the strains are small up to where dissipation takes place at the tip of the crack. In fact, the only place where energy is dissipated in this system is where material is broken at the crack tip. So everywhere around it, life is conservative. And all of the stuff that we really don't understand, this is the proverbial rug which we sweep all the stuff that we don't know under, is contained very near this singularity. Okay, now, if you solve the problem, again, solve the two wave equations with these boundary conditions, stress-free and displacement boundary conditions in front of the crack, this is what you get. You get this, like Inglis showed by squashing the ellipse, you get the same solution. You get a singularity that goes like 1 over the square root of r times some factor, which is dependent on the applied stress, on the instantaneous length of the crack, and on the crack's instantaneous velocity, times some universal angular function, okay? Now, cracks are stable, so you can have a crack, and even though it has a singular stress at its tip, it won't necessarily move. And why? Because it's not transporting enough energy to the tip in order to break bonds, to satisfy the dissipation at the tip of the crack. So a crack will move when the energy flux, which we'll call G for reasons that I've never understood, so the energy flowing in from the elastic fields into the tip of the crack is equal to the dissipation. And this dissipation gamma is called the fracture energy, and it's considered to be a material property. So this is something that each material has. And it's not just the cost to break a layer of bonds, as we'll see in a bit. Those of you who had enough coffee and are awake understand that already there's a large contradiction in this statement. Because how can I, on the one hand, assume small strains, and on the other hand, talk about the singular stress at the tip of a crack where all the good stuff takes place? And that's something that people didn't worry about until relatively recently. And I'll talk about that towards the end of this hour, where we have to extend fracture mechanics to nonlinear elasticity at the crack tip in order to better explain what's going on. Okay, sure. R is just the distance from the tip of the crack. So it's as you get closer to the tip, then the stress fields become more and more singular as 1 over the square root of r. Okay, any other questions? Because it's again, if someone doesn't understand something, usually about 90% of the audience doesn't understand the same thing. So, yeah. The stretches, here we're just doing a simple thing. We're pulling the stretches in one direction from the boundary, from the vertical boundaries. The R here is already infinity, basically. We're talking about an infinite system, right? R is measured from the tip of the crack. Okay. Well, the response of the material. Okay, let's separate two things. Nice, thanks you for the question. Okay, what we'll be looking at is the dynamics of this branch cut. Okay, and the dynamics will be very fast. We'll get very close to sound speeds. Okay, the material itself moves much more slowly. So the material, all of the material around here is actually organizing itself to get energy to flow to the tip of the crack to break bonds. And far enough away from the crack, this small strain is fine because you're not pulling anywhere near the theoretical strength of the material. So you're putting a big, the strains are small. The contradiction comes in the region where you're actually breaking things at the tip of the crack, because there you're stretching things enough in order to break the material. So you can't really assume that the material is linear elastic because you're breaking it. So that's where the contradiction lies. Any other questions? Well, I can easily answer that question by confusing everyone, but the mathematical origin is it's basically a Riemann surface, if you like. So you have people know what I'm talking about? It's a branch cut. When I was in kindergarten, they taught me this stuff, but we don't teach it very much anymore, so I'm not sure. So you have two. What does that mean? It means that if these two surfaces are the same surface, they're broken, but they're the same. If you relax the stresses, they're the same surface, but you have two different solutions for them. And mathematically, that will immediately give you a square root singularity. Now, where does it come from? Otherwise, intuitively, you can think of it as kind of like a scissors, if you like, where you have you're applying kind of finite stress here, but at the apex of the scissors, the stresses are amplified. It's not exactly the same mathematics, but it's kind of the idea. Any other questions? Yeah. I haven't even started yet. I'll talk, but yeah, I will. In fact, I'll give you an ad nauseum description of the equation of motion of a crack. But basically, the picture is that I'm applying stresses far away at infinity, and I'm dissipating energy at the tip of the crack. Okay, so somehow the energy has to come from here, the work that I'm applying, to here. So there's a flux of energy as the material organizes itself around this solution, basically. And the energy flows into the crack tip. And what does it do? It breaks bonds, or not. If there's not enough energy to break bonds, then the crack will just stay there. So, in fact, I'll do an experiment for you. I'm an experimentalist. Actually started my life as a field theorist, believe it or not. Calculated incalculable integrals for a living, and then wanted to know at the end of the day whether my calculations were correct. And when I asked the wise people around me, who I respected and still do, the answer was, well, it doesn't contradict anything. That was not the answer that I was looking for. So as a result, I decided to go into a field where I get the correct answers all the time, but generally I don't know what the question I should be asking is. So that's experimental physics. Okay, sheet of paper, nothing up my sleeves, as you can see. I've eaten very well while I've been here. A bit spicy, but very well. And I do this, and there's no way in the world that I'm going to be able to break this piece of paper. So this is tensile stress. Okay, now, if I make a small initial crack, so I'm creating the conditions for a singularity. Now, if I pull it very, very gently, this crack will be stable, nothing will happen, but it doesn't take much to do that. So you're just seeing the singularity working. That's what we're talking about. So even a small micron-sized singularity in a given material, the defects in the material will weaken it by orders of magnitude, which I just showed, and you can repeat this experiment when you get bored and of the rest of this talk. So it works also in your chairs. Okay, sure.
How do you define a crack? What I mean is this. Let's say you have a ductile and a brittle. And ductile is like you press and then it just deforms, and at some point it might.
Okay, hold that question. Great question. That's okay. If I haven't answered it within 3 slides, then ask it again. Okay. So yeah.
So when you first tried the experiment, I assume already there will be minute cracks in the material. Why they didn't initiate a propagation?
Okay, great question. We go backwards again. Because this coefficient of the singularity depends on the length of the crack. So if it's very small, the coefficient becomes small. And even though you have a singularity, you don't have enough energy to actually break bonds. So you always have small defects in the material, but this coefficient depends both on the amount of stress that you apply. So if you have a very, very small defect, you would have to apply a very, very large stress to get to some critical value, which is defined by this. I'll go into it a little bit more in detail, but this funny coefficient squared is basically the energy flux into the tip of the crack. So if this is too small, you won't be able to equate the dissipation, the amount that you need for dissipation, the crack, and a crack will exist. It will create the stress singularity, but it won't propagate. Okay, great questions. Thank you for them. Okay, so just for fun, for anybody that doesn't believe me, these are the theoretical strengths for a bunch of different materials. These are the practical strengths, and this is the ratio, orders of magnitude. And this is without actually making a macroscopic size crack. These are from the microscopic size cracks that always exist, the microscopic defects. And you can already see that the practical strength is much, much less than the theoretical strength. It's funny though, you can approach the theoretical strength of a material if you get rid of the cracks. With a 1 millimeter diameter glass fiber, you can lift a grand piano. It's strong enough. You can actually do that if you make fused fibers with 0 defects and you acid coat them to get rid of all the little cracks on their edges. You can lift incredible weights. Personally, I wouldn't stand underneath that grand piano though, but you can approach, if you're very, very, very careful, you can approach the theoretical strength of a material, but it's almost impossible, as an experimentalist at least. Okay, so the cracks focus this elastic energy into this stress-filled singularity and preferentially break bonds. And that's why we get this huge reduction in material strength. Okay, now to the question about ductile brittle. This is a picture, well, it's a calculation of this singular stress field here. So here's our crack. The stresses are color-coded. So blue is 0 stress. The initial stress is this light blue here, and this is our stress singularity, what looks like an ice cream cone or something, very pointy ice cream cone. So cracks are interesting as a physicist because they're really singular objects that propagate. As we'll see, they accelerate up to the speed of information in the material. So that's what makes them interesting, but also a little bit difficult to study. Now, back to this question, what's the difference between a ductile and a brittle material? Well, the thing is that nature does not really suffer singularities, not mathematical singularities. So the materials will act as the stresses become larger and larger in order to blunt the singularity. There's no real infinities in nature. Now, the only difference between a brittle material such as glass and a ductile material such as steel is how nature or how the material flows around this singularity in order to regularize it. And that's something that's not very well known, how it's done for different materials. For example, crystalline materials create defects. So you start to get more and more defects and dislocations. But glass, for example, is an amorphous material, so there aren't really any defects in glass, although the people in glasses might differ on that. A plastic, like, plasticky plastic or something, can be incredibly tough, something like polycarbonate, but that's also an amorphous material. So the way that the material organizes itself at the tip of the crack to blunt this mathematical singularity, and all the materials start to develop this as they get closer and closer to the crack, that will determine how strong a material is, or how tough a material is. Now, there are three different modes of fracture classically. So there's pure tensile fracture, so that's mode 1. And that's what I'll be talking about mostly all the time today, I think, is just pulling something under tension, under pure tension. There's also a mode 2 fracture, which I'll mention tomorrow and also when I talk about friction, and that's applying shear. So this is one material, and now I apply shear in this direction, and that's mode 2 fracture. These are all very close relatives, and mode 3 fracture is out of plane tearing fracture. So all of these exhibit the same stress singularity at their tip, but the coefficients are a bit different. Okay, so today we'll be talking about mode 1 fracture. So right now I'm gonna hand wave and derive actually a quite correct equation of motion. And to do that, I'm gonna follow the argument that was originally put forward by Neville Mott to explain the broken ships. Okay, so we're going back in history. And so here's our system. We're applying at an infinity it's a large infinite sized plate. Ships were big in those days. So we're applying some stress sigma infinity at the boundaries, again, under pure tension. We're assuming that the instantaneous length of the crack is L and its instantaneous velocity is V. We're also going to be assuming the following reasonable assumptions. Number 1 is that the crack is moving in a straight line. We're not letting the crack wiggle or do anything fancy. Single crack, moving straight ahead. The energy to break, the fracture energy, the energy to break a unit area of bonds here is considered to be constant, not dependent on the velocity or anything else, which is generally fine. And we're also assuming that energy is conserved in the system. That's all we need. Now let's use that to develop an equation of motion. Okay, so the total energy is just equal to the kinetic energy, which is dependent on the instantaneous length L of the crack, and also its instantaneous velocity V. The potential energy for a given crack length L times, now you're creating 2 new surfaces here. So if you have a bond, so if gamma is defined as the energy per unit surface that we're creating, so the total energy is 2 times the fracture energy times the length of the crack. Now we're saying since energy is conserved, once the crack starts to move, that's going to be a constant, and it's going to be equal to the potential and to the potential energy when the crack just started to move, when the kinetic energy is 0, and that started at some scale L0. So at some scale L0, the crack started to move. Its potential energy was just this, and the dissipated energy was just 2 gamma times the same length L naught. And this is now going to be conserved. Now we're going to solve this problem using dimensional analysis. So I'm going to hand wave. I'm an Israeli, we do this very well. So we're going to use the fact that all of the, this is an infinite system, so the only scale in the problem, the only length scale in the problem is the length of the crack L. So all of the fields, U is the displacement field in the material. They have to scale with L. So now let's just write down the expressions for the kinetic energy. So the kinetic energy is mv squared, rho is the density of the material. The temporal derivative of the displacement field is just the particle velocity, the motion at each point within this material. And we're integrating over all of that. So that's the kinetic energy, the motion of each point within this material. And we're assuming that the crack is moving at velocity v. So instead of a temporal derivative, we'll replace it with v times a spatial derivative dx. And then we'll make a jump and we'll say, okay, this has to go like v squared, this is the speed, times L squared, because we have a quadratic expression in the displacement field u, so it's VL times some constant of integration. Okay, now let's do the same for the potential energy. That's much easier. Why is it easier? It's a 2-dimensional spring, so we're pulling on it, and it's elastic material. So again, we have, this is the potential energy, this is the stress tensor, this is again the displacement field. Don't worry about them because again, this has to go like the displacement squared because again, 1/2 kx squared, it's a spring in 2 dimensions. So again, this has to go like, it reduces, the potential energy goes down as in the system as the crack advances, and it goes down like L squared times some other constant. The total energy then, this thing then just becomes this expression just by substituting all of this in. And again, it started, the crack initiated at a length L naught. So we just stick these with the same 2 constants or the same constant in this expression for the potential energy. Again, when it started, the kinetic energy was 0. Now, when does the crack start? We need one more condition. This is something called the Griffith condition. And the crack will start when the reduction in potential energy equals the cost to create a new surface. Okay, so that's just telling us that the derivative of the potential energy with the crack length at the initial crack length is exactly equal. This is the energy balance that I was talking about, is equal to the cost to create new surfaces. So this just gives us another condition on C2 and whatever. Now, if we just shove these in to this expression, this is a quadratic equation that even I can solve. So this is the answer. And this is telling us, first of all, that V, the instantaneous velocity of the crack, is equal to some constant, which we'll talk about in a second, times 1 minus L naught, the initial length of the crack, divided by the instantaneous length of the crack. Now, if you actually solve the problem, what you get is exactly the same expression or something. All of this stuff just has dimensions of length because this is the dimensionless quantity. And what does this even mean? Okay. First of all, it tells us that V equals 0 when L equals L naught. Well, that's what we assume. That's the initial crack length. So if the length of a crack is too small, well, this would give us V negative, which just means that nothing moves. Okay, so this is our threshold for fracture. There's a critical length, which is called the Griffith length in the system. If cracks are too short, you won't get propagation. This is also telling us that no matter how long, this can become infinite we have an asymptotic velocity here. Cracks can't go any faster than this constant. Now, when you solve the problem correctly, you find that this constant is something called the Rayleigh wave speed. Does anyone know what the Rayleigh wave speed is? I'll show you. The speed at which a disturbance moves along a free surface. Now, why does it have to be the Rayleigh wave speed intuitively? Because suppose the energy, the fracture energy went to zero. Do it like a turbulence argument, if you like. So if we look at this expression, for example, the fracture energy going to zero is equivalent to infinite stress here. So if I can get to zero in two ways. Now, if the fracture energy is zero, it means that the crack is actually moving as a disturbance and it's not dissipating any energy. That's exactly what this is doing. It's a wave moving along a free surface, and that moves the Rayleigh wave speed, and that's also the fastest that a crack can move. So now we can derive the equation of, now what we did here we used global energy balance. We calculated all of the energy through the entire infinite system, and without going into any details, just by waving our hands, we talked about the flux of energy into the crack tip. Okay, so the large scales are connected to the scale at which things are being broken. Now, yeah. Yeah, but we can even relax that and everything is still correct. Why should it be constant? If we were just breaking a layer of bonds and the force that we needed or the rate at which they were broken, the energy didn't really care that much, we would get a constant fracture energy. Mm-hmm. No, but the crack is even if you have a crack, it's always bounded by a region where there's no crack, right? So what you're breaking is the part where there's no crack. So it's the same amount of dissipation, if you want. Yeah, but we're assuming that we have initial crack that goes through the material, and that's already broken, we don't care. Right in front of the crack is where we want to break it, and that's pristine material. And that's where the fracture energy is coming from. Yeah. Mm-hmm. Yeah. They're the same thing, and I'll show you in a second. Okay, here we didn't mention anything about a singularity. There's no Griffith involved here. There's no stress intensity factor, if you like. But we can do the same calculation just here, because the only dissipation that's taking place is at the tip of the crack. So that's over here. So here's the tip of the crack. It's breaking stuff with a cos gamma. And this singular region is this, hope I have it written down here, probably not. Okay, this is the stress intensity factor, this K divided by the square root of R. Okay, how much energy, what is the energy flux into this? It's the stress times the strain. Both go like K over R over the square root of R. Stress times the strain gives you a K squared. And so the energy flowing into the tip of the crack is related to K by that expression. So we're still talking about the same thing. We're talking about a balance of energy flowing into the crack. This balance can be either local or global like we did before, but it's the same thing. Now we're just zooming in on since we know what the singular fields look like, as we get very, very close to the singularity, we can ignore everything else and just look at the singular fields. And that's classically what people do in fracture mechanics. What I showed you was the unclassical way how fracture mechanics was derived in the first place. But to do exactly the same thing is just looking at the flux of energy. Again, stress times strain, each goes like K over the square root of R. And when we do that, what you find is the same thing we just derived. So this is let me see, yeah. So if you do it microscopically, and actually this talk does talk about microscopics in that sense, then you get the same equation of motion. That's what happens when you do it the way that most people do it. So again, you have here the Rayleigh wave speed, 1 minus gamma, divided by the energy flux per unit area into the crack tip, which is G, and that's a function of the instantaneous length of the crack and the stresses that you apply far away. Okay, so some of the miracles of this equation of motion. So we've assumed linear elasticity until dissipation. Here's a scale where dissipation takes place. So linear elasticity dominates near this singularity here, near where it's trying to become singular. It gets cut off somehow near the tip, near at R equals 0, at the near where dissipation. Now there are many other contributions to the stress field. This is just the dominant one as we go close. And usually in fracture, because this is the easiest one to deal with, we talk about just the singular fields, and we ignore the higher order terms, which is fine. We've assumed an infinitely large medium, and when we do that, this equation of motion actually is very strange, because it's the velocity here is an instantaneous function of the length of the crack. There's no acceleration term here. It's almost like well, okay, first we have this asymptotic speed. Now V is first order in time, or with the crack. So the crack has no inertia. It's almost like a massless particle. So as a crack is zooming along, if, for example, you change the fracture energy, so it goes into a tougher material, instantaneously, this theory tells us that it will adapt its velocity to that material. There's no inertia. It doesn't take time, accelerate, decelerate. Accelerations and decelerations are instantaneous here because there's no V dot here. There's no acceleration term in this equation of motion. That's kind of weird. Let's check it experimentally. So I'm an experimentalist, so we actually did this a number of years ago. This one is in both glass and plexiglass. So these are the experimental results. This is the crack velocity. The sound speeds are, the Rayleigh wave speed is this line here, the dashed line. No, that's not, we'll talk about that in a minute. That's a different, the Rayleigh wave speeds here are up here and around 1,000 here for PMMA. And we went and for each one of these guys, each one of these things was initiated at a different stress, different stress, and the crack lengths were different or something, but we could take all of these things, use this as a filter, the equation of motion as a filter, and until these dashed lines, we find that we could use this basically to calculate the fracture energy. Just by, we know what the Rayleigh wave speed is, we measure the instantaneous V, we measure the instantaneous L, we know what this function is, we can calculate it. And using that, we collapse all of these measurements to well-defined curves. In glass, it's fairly constant, like as advertised. And in plexiglass, the curve is increasing slowly with the velocity. But again, That's fine too. Okay, so can we go home? Well, what happens beyond this critical velocity is that, okay, so this is the same measurement here. This one's for plexiglass, I think. And this is independently measured gamma, which I can tell you how we did it, but it doesn't matter. And here's where our collapse is. And over here, if we use the equation of motion, it's a total mess. Something is wrong. We have no measure of we can't explain why the fracture energy all of a sudden goes up and the equation of motion totally fails. And this happens at a velocity which is about 40% of the asymptotic velocity. So it's telling us something is wrong. And now I'll quickly tell you what is wrong. So what happens is that our simple crack becomes unstable. It undergoes an instability, which we called microbranching for reasons that you'll see in a moment. So at the point where the crack becomes unstable and the equation of motion stops working, so this is the crack velocity as a function of time below this instability threshold, and we see that it's to experimental accuracy, it's clean data. Now it starts to get a bit noisier as we get to this critical value where everything breaks down, and it becomes really messy at higher speeds. Now, if we look at the fracture surface, okay, now what's the fracture surface? This is our two-dimensional experiment, but it's not really two-dimensional. It has the third dimension. So we look at the surface that the crack has created, and that's what we're seeing here. Okay, so we have it's featureless basically below this critical velocity. And all of a sudden, at the critical velocity, you start to see structure appearing on the cracked surface. These little dots are they're not dirt, they're real things. And as we push the velocities to faster and faster, the structure becomes more and more apparent and larger. So if we look now from the side, so now we're taking our experiment and we're only going to look at half of it just because I only have two hands. So, and we're looking now from this direction through a microscope. What we see is that, okay, at this point where we have simple cracks, no structure, there is no structure. Everything is very boring. So we're looking just from the side here. These points here, if we look from the side, we see microscopic crack branches. So the main crack is going along this plane here, but we have these microscopic little guys that branch out and then die. So they're arrested cracks. And as we drive this crack faster and faster, they become much more dense and larger. And then we already have a lot of complexity here.
Can I ask how you
Sure.
took these pictures?
Oh, this was easy. Just with a microscope with an objective that gives me a very thin field of view. Just scanning from the side, looking pictures with light coming from the back. So whenever you have a crack, what it does is at the edges of the crack, they throw the light out in all directions. They're like very small lenses or something. And that's why you see black. And whenever there's not a crack, then you just see the light coming through. Yeah, these are, sometimes the experiments are difficult. This one wasn't. Just the idea of looking there was kind of new at the time. Okay, sure.
The first graph, that's crack velocity versus time, and the panel, the three graph panel, crack velocity versus the time again, but that goes from 0 to 15, maybe 20.
And the zero is just, it's not zero from the beginning experiments, it's just some arbitrary time. It's It's the same, it's a 15 microsecond window, that's all. Yeah, it's not, no, the real zero here was, this is probably about 100 or something, and it's somewhere in the middle of the sample.
Thank you.
Okay, any other questions? Yeah.
Depended or not? That's what I'm.
Wait, I would turn on the microphone too if we're already using it, just for fun.
Patterns are material dependent.
Good question. I'll answer it in a few minutes. The answer is no, but I'll show you for different materials that you have the same, exactly the same characteristics. But thanks for the question. Okay, now these instabilities are still, they've been seen numerically, but no one really understands them. So some of the best minds that I know of in physics have tried to find, and first people were looking at like many nonlinear systems for an instability. To cracks are stable to infinitesimal perturbations. Whatever you do, they're frustratingly stable. Okay, so according to that, these instabilities don't exist. We didn't really make them up though. If you look on, for example, a lattice or MD or finite element simulations, even phase field models, you see similar effects. You see an instability. People now are working to try to make it as quantitative as possible with phase field models, but you see it. So purely theoretically, these instabilities don't exist. In silico, they exist just like they do in experiments. And there's a size dependence here. I won't go into that, but yeah. So the bottom line is to understand these instabilities, you really have to know what's going on near the dissipative region. That's where all the good stuff is happening. When people perturbed a crack, they perturbed the linear elastic fracture mechanics crack. They didn't assume any nonlinearity at the tip because it's not clear what nonlinearity there is there. And when you do that, then no matter what you do to a crack, it'll just continue along the axis of symmetry. So there have been a number of empirical ways to model this dissipative region, some using phase field models, different types of models. There have also been attempts that were spurred by these experiments, actually, that took very good people to develop a theory of amorphous plasticity in order to try to solve this problem. Now, they haven't solved the problem, but one nice thing that came out of these experiments is we now have a lot of activity in understanding plastic materials, shear transformation zones and things like that. I don't know if many of you are familiar with this stuff, but a theory, a picture of amorphous plasticity has actually evolved directly from these experiments. Not directly, but the experiments kicked people into trying to get a fundamental picture of what's still going on, how materials, how the singularity is blunted, how plasticity arises in materials that don't have any structure to them. So now, the basic experimentally, the problem of tackling or cracking the fracture problem is that the velocities are so rapid that maybe when I was younger, I could take a microscope to look at the dissipative zone and run it like 3 kilometers a second, but I got older. It's become more and more difficult to run, probably with an AFM or something while I was doing it, tough thing to do. Also, the dissipative zone sizes are pretty small. In glass, they're considered to be nanometers, microns, and PMMA, or various plastics, brittle plastics and such. So it's hard to see something that's like really microscopic that's moving at the sound speeds of the material. Now, can we circumvent these problems? And well, yes, we can. And the way to do it is, and it came up in one of the previous talks, is to break Jello. Now, these are hydrogels. Now, I could have gone to the supermarket and bought the Jello and all that, which is kind of yucky or something. But since we were paid a lot of money to do this, we broke scientific Jello. So I'll tell you about that in a moment. In fact, many of you that are working in biophysics know this stuff. It's polyacrylamides. These are gels that are typically used in electrophoresis to look how large molecules are. You run them in an electric field through an obstacle course. The obstacle course are these gels. I was doing some bio experiments at the time, and we have slippery fingers sometimes, so we dropped some of these plates and they shattered like glass. And this brought up the idea is maybe they're shattering like glass because they actually shatter like glass. So we started to work with these. So these polyacrylamide gels, we can tune the chemical composition with them to various, and we have, but basically the Rayleigh wave speed goes down from kilometers a second to meters a second. Now, meters a second is already tractable. So the experiments that I'll be talking about in a second were done with these gels, scientific Jello. But first I have to prove to you that everything that happens when you break Jello is exactly the same as what happens when you break glass or plaster, brittle plastics. So it's not just an analog experiment, it's a real experiment just slowing things down. So that's the first thing that we're going to do. So this is a schematic of the experiment. So you have like a thin plate of a sheet of this Jello, which we molded. You illuminate it from the bottom and look through a fast camera. So immediately you can see the crack tip as it's moving. You can measure the parabolic structure at its tip. We've patterned the surfaces here. So we can use something like particle tracking or DIC to measure actually the strain fields throughout the system. So we can just looking at how particles deform. Eventually we went over to tiny little grids that we imprinted on one of the surfaces. So each snapshot of this, of the crack will give us the entire displacement field. And we can take derivatives and get the stress and strains and all this kind of stuff. So just by slowing things down, we can do things that people never imagined that they could do in this business. So first I have to show you that, okay, this is our instability. So this is a crack. Now here 0 is the beginning of the experiment, okay? And so this is a comparison of brittle gels and glass. So we have something that's relatively well behaved until it gets to about the same critical velocity, about 0.4 of the Rayleigh wave speed. And then it starts to wiggle just as here. So we find that the dynamics appear the same. If we look from the side at our samples, remember now we're looking through a microscope this way, okay? What we find is that this is in plexiglass, this is half of an experiment in glass and half an experiment in polyacrylamide. We see the same features, and not only that, they have the same functional form. They're approximately, I don't know, y, it goes like x to some power 0.7 or something. Yeah.
Crack tip velocity, that is actually varies with the crack length. That increases and then saturates.
These peaks.
Yeah.
Yeah, that's part of, because what's going on, thanks for the question. These microbranches are disappearing. So whenever remember I told you that the equation of motion has no inertia. So if instantaneously we're back to a simple crack, no branches, anything, so the crack dies. So for 1 microsecond, the crack will jump to where the equation of motion tells it to go. And that's why we have this locus of, this might be noise, I'm not sure, but we have a locus of peaks here. And each one of these peaks, we've actually done this experiment, corresponds precisely to what the equation of motion should tell us. Because, again, instantaneously, we're back to having a simple crack. Okay, but the structure that they create is identical. And even, this is now a picture of, again, the fracture surface that were created here. And this is in gels, and this is in glass. And you find that these microbranches, this is the top part of the microbranch, and it goes into the material, but you can't see it here. They actually are very localized in the z direction, in the direction that's normal to the propagation direction, and they look the same as in glass as well. So the same, anything that we can use to empirically characterize fracture in these materials, we see in these materials. So as a result, we turned over and we're just using these materials to understand things that there's no way that we could even get close to in more standard materials. This is just for fun. This is a movie of a crack propagating up to about see it on here? Ah, good. Okay. This is the time. This is a clock in milliseconds. This is our crack moving around. It's now branching. It's also micro branching here. This is the roughness. And okay. Now, just to show you that we can do these experiments, we really do see up real cracks. Now, empirically, we can suppress crack branching in gels. And how do we do that? Because gels are, they're basically noise triggered, these instabilities. So these are the micro branches. So they started here by because the crack front, which is moving through the material, got kicked here and here, so they started. Now, they have a minimum width to them. They don't expand over the whole surface, each one of these lines of microscopic branches. And when one of these guys hits an edge, this is a free surface. So this is either this or there, and they disappear. So as a result, if we make these samples thinner and thinner, we can get to a point where there are very few of these micro branches. They disappear, and we can have long sections where we have simple cracks once again. And when we do that, for example, we can test the equation of motion beyond the onset of this instability. And we'll do that in a second. So right now, and these single crack states, as I'll show you, can accelerate to nearly the Rayleigh wave speed. Now, when we did that, we got a surprise. Okay, we expected that when we get rid of all the instabilities by suppressing them, that we can that we would see cracks smoothly accelerating up to the Rayleigh wave speed and just stay there, and everybody would be happy. What we found is we got cracks that smoothly accelerated up to the Rayleigh wave speed, and then slightly beyond the Rayleigh wave speed, something funny happened. And I'll show you what that is. So here's our crack. It's going faster and faster. Smooth, not branching, and then all of a sudden, at about a little bit beyond the Rayleigh wave speed, it starts to oscillate and wiggle. So this is one reason why I stopped doing theoretical physics, because my mind isn't fertile enough to guess this would happen. But if you just ask nature, nature tells you this is what I see, and then you have to think where this is coming from. So this is a new instability. It takes place at about 90% of the shear wave speed, 95% of the Rayleigh wave speed, actually. And now, let's forget about these instabilities. And in the last few minutes, I'll go back to simple cracks, and we'll see if we can understand simple cracks a bit better. So we're going to suppress all of the instabilities, and we're going to measure the structure in the singular region as close to as we can get, and compare it to what the classical theory tells us, the singular theory tells us. So the first thing I want to show you is here, this is the equation of motion that we derived before. This is it in nasty detail or something, but it's dependent. This is the fracture energy, well, whatever. This is the fracture energy again. It depends on the instantaneous length of the crack, and this is the velocity. So this is the velocity as a function of the length of the crack. And for each one, the different colors are different stresses that we applied at infinity. And the points are the data, and the straight lines are the theory with no adjustable parameters. So once we've gotten rid of all of the things that we don't understand, it tells us that the theory understands very well what's going on. Okay, so the equation of motion works nearly up to its asymptotic velocity. This is an equation of motion that we derived for an infinite system. Remember the Mott thing. Just for fun, and remember an infinite system, cracks have no inertia. Well, I don't know. Okay, I'll take a minute. If we have different geometries, suppose we break a system like this, which is an infinite strip. It's a long strip, but it has vertical boundaries. So the crack, as it's propagating, it can send out waves. The waves bounce off the boundaries and come back and interact with the crack. In this case, the crack has to have inertia because it knows about what it did beforehand. Information is not being propagated out to infinity as in an infinite system, but it's bouncing back and interacting with the crack. So the crack's history is coming back and interacting with its present. So when you calculate this, and my friend Mike Martyr did this, he derived this equation of motion in the early 90s, and everyone kind of ignored it because it didn't seem to agree with the classical equation of motion. And one salient fact was that a crack, it's still limited by the Rayleigh wave speed, and the reason it does is because it develops an effective mass. This is a singular term that explodes when the velocity approaches the limiting wave speed. So the crack gets heavier and heavier. Actually, it gets inertia, but the inertia is what in this model or in this prediction limits the speed, and it actually seems to work. So this is our infinite system, and B is the length, is the width, or the vertical size of the system. And when the crack gets to this scale where information starts to bounce back and interact from the boundaries, which is the scale B, then it changes its motion, and this straight line is exactly this prediction, again with no free parameters. So we have two equations of motion that work under different circumstances. Both of them assume they're basically driven by energy balance. So the energy that's flowing into the tip of the crack is equal to the fracture energy, just different implementations of the same principle. Okay, so let's go back to our singular fields, and we're going to use these gels in order to zoom in and try to see where the singularity breaks down, okay? Because it has to break down somewhere. How is nature doing it? These things are so slow. So here's a cartoon of the parabolic profile that's, this is the same K that's the singularity. The displacement fields at the boundary are parabolic because the derivative of this gives us the strain field or the stress field. So the displacement in the y direction here goes like the square root of r. So we have parabolas on their side. That's what things should look like. Okay, this is a cartoon. This is a snapshot of a crack moving at about half of the Rayleigh wave speed where we suppressed all of the instabilities. And this is a fit to this theory. And, you know, it seems to work actually pretty well. We described this, and this K is not a free parameter. It can be derived from the fracture energy, which we've measured. So no free parameters, everybody's happy. But then we got greedy, as physicists tend to be. So we decided let's look closer. And what we find if we look closer is that if we expand this, there's a region where the parabola doesn't quite fit. Okay, who cares? Okay, it turns out that there's some scale here, which were just the distance from the apex of this parabola to the apex of the real crack, just empirically defined it, where this typical, where the solution doesn't work. Now, what is this scale? Is this the scale of dissipation? We thought, okay, we're looking now at how nature is blunting the stress singularity here. Or could it possibly be a nonlinear elastic scale? Why nonlinear elastic? Because we're pulling the material so hard, so much that linear elasticity can't hold anymore. So how can we check? We just looked at the dependence of this scale with the crack velocity. And this scale is actually a very highly nonlinear function of the crack velocity. It gets larger and larger the closer you go to the asymptotic velocity. And at the same time, we measure K by just this parabola. So we measure using each snapshot, we can measure the fracture energy or the dissipation, and it's fairly well behaved. So if this were some symbol, some characteristic of dissipation, we would expect that this thing to be as well behaved as this, but that's not what we're seeing. So as a result, we decided that this is actually nonlinear elasticity and not dissipation. And then we used that. Okay, so to decide is one thing. Sometimes theorists are useful. So my friend Eran Buchbinder, who was at the time a postdoc in my group, and I didn't have anything for him to do because he was a theorist. And as we all know, theorists are basically useless. So I told him, you know, take a look at this stuff and see if you can figure it out. Figuring I would get rid of him because he was asking all these embarrassing questions all the time. So he came back, and you know, after a month he came back and he says, I think I have it. So we looked at it, and no, he had it wrong. Okay, so I sent him away again, and he came back a month later, and this time I really have it. And he did, and I'll show you what he came up with. So by the way, if we look at these experiments and compare them as a function of velocity to the predictions, this is the linear elastic fracture mechanic prediction of the strain field. So we find that the faster we go, the worse the prediction, the theory seems to get. In fact, this one tells us that cracks should be under pressure, not under tension as you approach the tip. Something, and these are what we actually measure. So Eran said, you know, what he actually did was he re-derived fracture mechanics from scratch in a perturbative way using nonlinear elasticity. So assuming a nonlinear piece of Hooke's law. Okay, there's going to be some details here, but that's what we're talking about. So in gels, we can measure the stress strain curve, and it looks kind of linear. Stress strain, these are the gels that we're using. If you wake me up at 3 in the morning and say, is that a straight line? I would say, yes, go away. But if you do it carefully enough, you find that at strains of about 0.1 or something, the stress strain law, which is called for neo-Hookean materials, this is what it actually should be. It does deviate from linear elasticity. a small deviation. So what? Again, he didn't have anything better to do, so he was working hard at trying to solve this. So he extended LEFM to include this weak nonlinear elasticity. Now, why the materials have to become, or why the nonlinearities have to be relevant? Forget about gels. For any material, this is your potential curve. Hooke's law lives here, where the potential is parabolic. That's why Hooke's law or Young's modulus are irrelevant for small strains, because you're always talking about something near a minimum, and all minima are nearly parabolic, very close to the minimum, and that's where stress strains are linear. Now we're talking about fracture. We're out here someplace. So obviously we need to take corrections to this parabolic potential into account, and that's what Eran did. So, okay, I have 5 minutes. Let me go very quickly through the details. So he found a small parameter, which is just the ratio of the linear. This is the stress strain. This is Hooke's law, and the ratio of the linear and first quadratic nonlinear terms. And then he solved fracture mechanics. This is just Newton's law written so no one can understand. F equals ma for a field, and that's linear elastic fracture mechanics. So he solved this problem, and then he used this solution, of course, to solve the second order problem, which looks much nastier, but it actually can be solved almost analytically, or mostly analytically. And nonlinearity becomes significant at some strain, in this case of about 0.1. And this strain where nonlinearity becomes significant defines a length scale, how far away, and this length scale here is determined dynamically. So as the crack becomes faster and faster, this length scale depends on the instantaneous velocity of the crack. This is the solution. You can stare at it all you want, but the salient parts of the solution are that actually, instead of regularizing the square root singularity, the singularity becomes worse. It becomes like 1 over r instead of 1 over the square root of r when you take into account nonlinearity. It also has logarithmic terms in the displacement along x, and you get this existence of a dynamic length scale that depends on the nonlinear coefficients, on the second order nonlinearity. Okay, so let's compare it to theory, or to experiment. Now this theory has no adjustable parameters because we can measure everything, and we did. And what we found is the blue lines are the theoretical description, and they actually pass through the points. The black dots are classical fracture mechanics. And so it was worthwhile having a theorist around and sending him away to calculate things, turns out. He's been doing it very well since then as well, for his own group. But sometimes theorists are useful. That's probably the bottom line of this talk. Often not, but sometimes there's a use for them. So if we go back to simple cracks, this is the parabolic form of just the garden variety crack. This is what LEFM tells us. This theory, it has to be cut off here because it's a perturbative expansion. As you get closer and closer to the crack tip, it's not controlled anymore, so we can't use it. But what we did was we derived actually a theory just for very, very large strains where the equations actually become much simpler, so you can solve them analytically at this point here. So we have, the bottom line is we have a really, really good description, theoretical description of very, very boring cracks. Okay, so these are these are simple cracks, no instabilities, no anything. And Now, and the next, okay, this is just a preview for tomorrow. Should we live so long? Okay. We'll talk about using this nonlinear length scale to actually understand instabilities. And it turns out that the physics at small scales, at the smallest scales near the singularity, are incredibly important if we want to understand actually the macroscopic behavior of materials as they break. Why all of this stuff, these are tiny little branches, they're small themselves, but they increase dissipation by an order of magnitude. So if we don't know about them, then all of a sudden we find that that a crack dissipates more and more energy for basically no reason discernible to eye. That's a macroscopic effect. The microscopic effect is because you have, for example, this instability. What causes this instability is something even more microscopic, this very small region of elastic nonlinearity near the crack tip. So that's where we're going tomorrow. And there should be a thank you somewhere. Okay, yes. Okay, so this is what we've just done. We've derived an equation of motion. We've understood simple cracks much more than you would ever want to. And tomorrow we'll be looking at crack instabilities using this nonlinear scale. Not next week, but tomorrow. But thank you for your attention.
Thank you for this lovely talk. And so what we have learned is theoreticians are sometimes useful. When you become old, then you switch from theory to experiment because you want to see ready-made.
I was quite young when this happened, actually, and I still am. But I've been 48 years old for a number of years now. I just want you to know that. But
so correction there, 48 years old now. Mike, I have a question. So I take the liberty and ask the first question. When I was very young, there was some oil drilling. I come from the northeast part of India, and they blasted the earth down, and our house everywhere cracked.
yeah,
And so my father has to, build a new house. At the time, I was so sad. I was thinking, oh God, do something and just make it okay so that my old memory remains there. And then very recently, I heard one news from Kolkata. There is an old bridge, steel bridge, iron, and there was a crack, observable crack, and then after a few days, it was gone. So it's self-healed. So what my question is, so there are some material like the concrete that don't, as far as I know, and there are some material that do, like this Kolkata example.
I'd like to really see how that one happened, but yeah, okay.
Yeah. So is there any understanding what makes some material to self-heal cracks and some materials which would never do that? Thank you.
Good question. Again, I would not really take a 10-ton truck over that bridge. Just me, maybe others are braver. If you break, for example, glass in a vacuum, and you put the pieces together, they will reheal perfectly. Glass, silicon, because what prevents the rehealing is basically oxidation of the crack surface. You change the chemistry of the surface. So if you have a high vacuum, you do it, and you haven't changed the chemistry, there's no reason why when you put them back together, they will reheal. There is a large effort now in soft materials to create soft materials that will fix themselves. Number of groups, the one that pops up is an ESPCI in Paris, where Constantine Creton's group and others are working on actually putting in like nanoparticles as cross-linkers. So they're reversible so you pull them apart, but you haven't broken any chemical bonds. They're still kind of sticky, so they come back together again. And this is really good for performing operation for glue. If you're cutting your tissue and you want to glue it or something, it's actually very useful. I'm not sure if it's carcinogenic or not. That's not my field, but you will stop bleeding. You might develop cancer, but that's another problem. So yes, there's no real reason why cracks can't heal except by irreversible deformation of the surfaces where you can fit them together. Sorry about your father's house. In fact, the hydrofracking is one way. If we all stick around to my third talk, I'll talk about friction earthquakes, and it's related to this stuff. But some of the most seismically active areas in the world are where they're doing hydrofracking. And you're exciting pre-existing cracks or faults that no one even knew existed, and all of a sudden you have earthquakes that are totally unexpected. Now, this is not something that gets to the newspapers that much because there's multi-billion-dollar, trillion-dollar industry involved, and they don't really want you to read about it, but it does happen.
You talked about branching. So there are two ways I think branching can happen. One is your single crack can split into two ways. And second is there is a crack, but then after the formation of crack, there is a crack forming perpendicular to the direction of the previous crack. What is the difference between these two branches? Are they same? Or?
We'll take a closer look at branching tomorrow. You'll find that it's not actually a bifurcation. It's what I hope to show you is actually it looks like a bifurcation. You have a crack that's curving within the depth of you have at one Z location along the crack front. You have a perturbation that causes the crack to curve out of plane. The other one goes straight. If you look at both of them from the side, it looks like you have a bifurcation, but it's not. You can sometimes in nature see perpendicular cracks. For example, mud cracks and drying. But often the perpendicular cracks are caused by networks of one crack, and then it splits the material in two, then it keeps drying, a second crack, and then another crack. So they don't happen at the same time. So it's a sequence, but there's still a lot of things we don't understand, and there are many aspects of that problem which we don't understand either.
Thank you.
Last, we started a bit late, so maybe we can take a bit more time.
I'm here, I don't drink that much coffee either, but I'm sure everyone wants to, but happily.
So this is a quick question, Jay. This nonlinearity arises in brittle materials, you say, like your slide says. Is it a material dependent property, and does it show up in ductile materials too, or do those obey linear elasticity reasonably well?
The opposite is true. Okay, first, the answer to everything is yes, but that's the short answer. First of all, any material, no matter what it is, if it has some kind of a potential energy curve that's not parabolic, you're going to have nonlinear elasticity. It has to happen. The coefficients, if you do a perturbation expansion, are going to be different according to whatever potential you have, but they will be different. Now, ductile materials are also nonlinear elastic, but they have a different piece to them where they have plastic deformation, because nonlinear elasticity means that, okay, the stress strain curve is not a straight line, but if you relax the stress, it'll go back to where it was. It's conservative. Ductile materials obey that to a point. And then at some point, they also plastically deform. And that's a different animal. And that, when that happens, is very material dependent. It's not clearly not entirely understood in many amorphous materials. It's known that it happens, but can you predict that from first principles? It depends what your principles are. But people are working on it as we speak, actually. But that's the difference between plasticity and nonlinearity. Although historically, they've all been lumped together under the same rug. Okay, this is anything that's not linear elasticity we don't understand. So now we understand a little bit more, is what I'm